Now we have Tamra Nebabu, who will tell us about a general protocol for bulk reconstructions from generalized free fields.
I'd like to begin by thanking the organizers for giving me the opportunity to speak today. And what I'm going to be talking about is a generalized protocol for bulk reconstruction, which is an ongoing work by Xiaoliang Qi and I. And in particular, we are able to develop a bulk reconstruction method that allows us to construct the bulk for any boundary model that contains generalized free fields. So I'll begin briefly by motivating bulk reconstruction. So bulk reconstruction is of interest in the context of holographic duality because it allows us to map observables on the two sides of the duality and in particular construct the bulk observables from the boundary data. And this is enabled by the fact that holographically dual models should have isomorphic Hilbert spaces. So there should be a unitary that relates them. And the bulk reconstruction is actually facilitated by a dictionary that allows you to map boundary states and operators to those in the bulk. And this is of interest because it allows us to describe things like the emergence of bulk locality and geometry from the boundary perspective. Now, there are several known approaches for bulk reconstruction, but the one that I'm going to be focusing on or giving a brief overview of is HKLL, because it is the sort of inspiration for the more general approach that we develop. Okay, so I'm going to begin with an overview of HKLL reconstruction, and I'm going to talk about how we are able to generalize it without invoking any knowledge of the bulk geometry. And this work is unpublished, but hopefully we'll be putting it out soon. And I'll show how our reconstruction approach can be used in a particular case study of the SYK model. And I'll show how our reconstruction approach has evidence of producing a sensible bulk description by examining some features of the bulk and its geometry that we recover. In particular, we're going to see that we discover a bulk bath that kind of behaves kind of like a horizon. We're going to be able to deduce features of the curved geometry that we get, as well as evidence for topological properties of the geometry associated to the thermal field bubble, shockwave, and traversable wormhole cases. And lastly, I'm going to conclude with some open questions in future directions. Okay, so what is HKLL? HKLL stands for the initials of the authors of the original seminal papers that were published from 2005 to 2007. And in particular, it's a bulk reconstruction protocol that writes bulk operators as a linear superposition of boundary operators within the causal wedge. And the linear coefficients of this superposition are known as the kernel or smearing function, and I will be denoting it by K. In this expression here, phi is being used to denote the bulk fields. Script O is being used to denote the boundary fields. Z is the extra bulk coordinate, and X is all the remaining boundary coordinates. And here I have a cartoon of what the kernel support should look like in the case of 1+1D bulk. And the second main ingredient for HKLL reconstruction is the extrapolate dictionary, which essentially tells you how your bulk field should behave as you approach the boundary. And in particular, if you have a CFT boundary theory, if you take your bulk field and you scale it by z to the minus delta, where delta is the conformal dimension of the boundary operator of interest, as you take the coordinate z to 0 at the boundary, you should precisely recover the boundary conformal operator. And this is how the boundary data enters in and allows you to find the kernels. So how do you actually conduct HKLL? So you start off with free fields living in some sort of semi-classical bulk geometry. And in the context of ADS CFT, you start off with free fields in ADS. As an example, if you're working in ADS2, with a metric as given here in global coordinates, you can retrieve the bulk equations of motions for a scalar field as given by this expression here. And HKLL tells you that you can find the kernels by generically considering the set of solutions to this equation of motion, and then imposing the extrapolate dictionary as the boundary conditions which fix your bulk fields. Now, I'm going to skip over the technical details of how this is done, but if you're interested, you can ask me later. The upshot of this is that by plugging in the kernel expansions, you can write any bulk correlator of interest as a sum over the boundary correlators. Oh, yep. And one more thing I should say is that you can actually back away from the free field limit and add back in interactions perturbatively. So you'll notice that when I talked about HKLL, I made reference to the bulk equations of motion. But this is ideally something we don't want to make reference to for a bulk reconstruction protocol if we truly believe the bulk to be emergent. So you can ask a question, which is, can we reconstruct the bulk without assuming the geometry and the equations of motion? So what we're looking for is some kind of procedure where we feed in boundary data in the form of the operators and the correlation functions, and we get out all the things we want to know about the bulk. So it's operators, the dynamics, as well as the geometry. And the answer of whether or not this can be done is yes, at least in the restricted cases that we consider. Okay, so this is the take-home message in one slide. The claim that we're making here is that given a boundary theory with generalized free fields or GFFs, and using only their 2-point function data, and demanding some very natural restrictions on the kernels, which I will explain later, you can actually produce a Gaussian quantum circuit that represents the bulk operators and their dynamics. And this fully captures the information of the bulk that we want. And in particular, it actually is able to encode some geometric features of the bulk without knowledge of the equations of motion a priori. So for the remainder of this talk, I will be focusing on the case of a 0+1 dimensional boundary dual to a 1+1 dimensional bulk. But in principle, our reconstruction protocol is applicable in higher dimensions. I will also be focusing on the case of fermionic boundary and bulk fields because we're going to be examining the Syk model as a case study. You'll also notice that I've drawn discretized points along my one-dimensional boundary line. And that's because to explicitly implement our reconstruction, we're going to need to discretize space-time. And this is not actually detrimental to extracting some universal physics that we expect to hold in the continuum limit. And I will be showing evidence of that. But in principle, you might also be able to extend our protocol using some more fancy mathematical machinery involving von Neumann algebras. Lastly, I should mention that even though I'm going to be focusing on fermions, everything can be straightforwardly applied to the case with bosonic operators. All right, awesome. So how does our bulk reconstruction protocol work? So as I mentioned before, we're going to be starting off by discretizing space-time. And so for our one-dimensional boundary, that just corresponds to discretizing time. And then we're going to make an HKLL-like linear ansatz for the bulk fields. So here I'm denoting the bulk fields by psi, the boundary fields by chi, and I'm going to be using this notation for the remainder of this talk. And k represents the kernels that we're trying to find. And so in order to find these kernels, we're going to impose two constraints. And the first is that we're going to demand a compact kernel support within the causal wedge of the bulk point of interest. And that can be seen here by just restricting the times that we're looking at. And it turns out this is equivalent to imposing a bulk causal structure in the direction perpendicular to the boundary. Next, we're going to be imposing a bulk operator algebra on any Cauchy slice for which we want to find the kernels of the bulk operators for. So in particular, if we have fermionic boundary operators, we also want to have fermionic bulk operators. And so we want them to be anti-commuting on a Cauchy slice because they are space-like separated. And it turns out that these two conditions are sufficient to uniquely pick out a kernel in 1+1D up to a local basis change. Okay, so you'll notice that I've made reference before to creating a bulk Gaussian quantum circuit representation, but in the actual description of the protocol, I made no mention of a circuit whatsoever. And that's just a consequence of the fact that in 1+1D, if you have a semi-infinite bulk with a boundary, as long as it has local dynamics, you can actually show that it can necessarily be represented by a local quantum circuit. And this just comes from a result from a 2011 paper on cellular automata. And the reason we know we have local dynamics in the first place is because of the bulk causal structure that we imposed in the first constraint of our kernel. You can show that that is sufficient to prove that any pair of bulk operators that are space-like separated should be anti-commuting. All right, so now that we know that we can describe our bulk by a quantum circuit, I can now freely draw circuits as I please. And in this picture, we can examine the two conditions. The first is that given any bulk fermions, such as those indicated by the pink and orange arrows, the support of the kernel should exist on the boundary interval corresponding or spanned by the edge of the light cone in the respective colors. And condition number 2 for the bulk operator algebra is simply that for any Cauchy slice, of which many examples are shown here, we want the bulk operators to be anti-commuting. All right. So the claim I made earlier was that the boundary 2-point function data is sufficient to build the bulk quantum circuit. And the reason that's the case is because we're assuming that we have a boundary that can be described by generalized free fields. And generalized free fields are simply fields that satisfy Wix theorem in a particular state. So for example, if we have some boundary fields chi, and we're computing the 4-point function, it should be factorizable as a product of 2-point functions. And what this implies is that the corresponding bulk fields should also be factorizable. So we get Wix theorem in the bulk as well. An interesting known example, which will be of relevance to us, is the SYK model in the large N limit. Before I move on, it's helpful to standardize some notation. So I'm going to denote the Whiteman 2-point functions by capital G. This is going to be a matrix that tabulates the 2-point functions. The anti-commutator contribution to that is going to be denoted by capital A, and the commutators are going to be denoted by capital C. So I already mentioned that we're going to be using the anti-commutators to impose the bulk fermion algebra. And it turns out the commutators are going to give us information about the bulk state. So now that we have a circuit description, we can more precisely denote the two constraints in the language of matrices. So imposing the bulk operator algebra simply amounts to satisfying this matrix equation, which is that KA transpose is going to be the identity on the Cauchy slice. And the requirement for support only on the space-like separated wedge. If you cleverly choose the cut in your circuit like shown, amounts to imposing a structure on the shape of the kernel of the non-zero entries. So for example, if you're looking at the kernels associated to the bulk fermions living on this particular cut in the future light cone, that tells you that your kernels should be lower right triangular, and similarly, the kernels describing this lower or past light cone should be lower left triangular. Okay, so how do you actually find kernels that satisfy those two constraints? It turns out you can do so pretty straightforwardly using QR decomposition. The caveat is that this requires your anti-commutator matrix to be non-singular, and this is a point that I will return to later. But this just tells us that in very generic cases, this reconstruction protocol can be done. Okay, so you can actually ascribe a physical interpretation of our reconstruction. So this is a picture you should have in mind. You start off with your boundary operators, perhaps n of them at time equals 0, and you build up the bulk by considering or adding up the boundary operators at different times. And these are going to be linearly independent sets of operators with respect to the anti-commutator. And as you go on in time, you fill up operator space. And this is facilitated by the fact that the dimension of your operator space is much larger than the number of operators at each boundary time point. So n is much smaller than the dimension of your operator space. All right, so now that we have a kernels for a particular Cauchy slice, because you can do so for every Cauchy slice, this means you know all the kernels associated to all of the lines in your circuit. And this also tells us we can deduce what the gates are. So in particular, since we know the inputs and outputs, bulk operators to every gate, we can simply write down what these unitary gates are in terms of the kernels. So now let's actually look at an application of our protocol to the SYK model. So briefly, the SYK model is a model of n Majorana fermions with Q-body interactions among them. The Majorana fermions are defined to satisfy the fermionic algebra as well as a hermiticity requirement. And I have a cartoon here kind of showing the fact that we're considering all groups of Q among the n fermions in our Hamiltonian. Now, these coupling constants are disordered, typically Gaussian with a particular variance that makes large n suitable. And usually we're considering ensemble average quantities in this model. Now, there are many interesting features I can tell you about the SYK model, but the key feature that is going to be relevant to us here is that we have generalized free fields that satisfy Wix theorem to leading order in 1/n. So what this means in particular is that, for example, the 4-point function of 4 Majoranas can be factorized into the Wix theorem part, as well as another part that is at 1/n. So in the remainder of this talk, we will be using the large n analytic 2-point functions computed in a previous paper when doing numerics, and we're going to be sampling it at different times so that we can find our kernels and do all the things I told you about before. And we're going to be considering the correlators in the thermal field double state. Okay. So the thermal field double state of the SYK is known to have exponentially decaying 2-point functions at finite beta. And what this implies is that our dual bulk circuit description at finite beta must also be able to reproduce these exponentially decaying correlations. And a sneak peek is that we're going to be able to ascribe a geometric reason for these exponentially this exponential decay. So at large n, we actually have an exact forms of Wix theorem, which means only the diagonal components of the 2-point functions matter, which means that the U and V gates in our circuit simply become 2x2 matrices. So it suffices to parameterize them by one gate angle. And this is how we're going to denote them with the 2 types of gates at the integer and half integer locations, having gate angle theta U and theta V respectively. And so now we can actually take a look at what that gate angle is as a function of depth into the circuit, spatial depth. And we actually see something kind of interesting, which is that the gate angle exponentially approaches pi/2, which means that the U and V gates approach the swap operator as you go deeper into the bulk. So this is kind of a cartoon of the picture you should have in your head for the circuit. So you have some non-trivial gates up to some characteristic correlation length in the bulk, and then after that, you just have a swap. And you can basically think of the circuit after a certain point as just being a big old swap fest. So this approach to swap happens exponentially in the depth, and you can look at the dependence of this correlation length as a function of beta. And indeed, you get something that agrees with intuition. So you find that this characteristic correlation length increases linearly with beta. And this actually agrees with our intuition because once a bulk operator mode reaches the edge of this swap regime, it's going to flow out, never to return, and not influence the boundary correlations. So this is the geometric reason for the decaying tails. And we also, this linear behavior is expected because at high beta, which is the low temperature limit, we expect the horizon to shrink back down to give our regular thermofield double state. But at finite beta, this is pushed out or stretched. So again, just to reiterate, the picture that we have is that at a certain vertical line, we get swaps. And you can think of this as a stretched version of the horizon that you get in the Penrose diagram. So this vertical line actually corresponds to a hyperbola, and the spacing in the z direction gets infinitely closer as you probe deeper into the bulk. And we're actually going to be able to make more precise statements about the geometry later on. So next, you can examine the different modes that are falling into the horizon. And it turns out, if you look at the kernels for a particular bulk fermion at a particular point, they kind of look like localized wave packets. So you can actually very literally think of them as modes falling into your horizon. And you can actually show that these bulk operators are invisible with respect to the boundary correlators. So what do I mean by that? So if you consider the bulk operators, but instead of labeling them by their circuit coordinates, you label them by the 2 times that span their light cones. If you take this one to infinity, by construction, you know that it's the kernel of the bulk operator is going to be such that it anti-commutes with everything in its wedge, and that means it anti-commutes with the whole boundary. And furthermore, using that and Wix theorem actually shows that if you apply such an infalling mode to your state, the state becomes indistinguishable from the state without the infalling mode applied. So this represents the invisible or protected quantum information that is inaccessible to the boundary observer. All right, so now we can have a more fine-grained look at the geometry and get something that looks like ADS2. So any metric in 1 + 1D can be written in this form. So it's conformally equivalent to the flat metric. And the free Hamiltonian for the Majoranas is written here, where we identify the R subscript and L subscript Majoranas with the left movers and right movers in our bulk quantum circuit. Now notice that this conformal factor appears with an M in conjunction in just the mass term and not in this term because this part is conformally invariant. So now that we have this Hamiltonian, we can actually use this to find the time evolution, which I denote by little u to distinguish from the gates for time delta t. And we can compare this one with the physical time evolution from our circuit, which corresponds to 2 layers of gates. And when we consider the flat case where this conformal factor is simply 1, we can actually deduce a relationship between the mass and the gate angle. And assuming that that same relationship is going to hold in the curved case is going to allow us to deduce features of the geometry. So in the limit of long spatial frequency and small delta t, we can actually recover M exactly. And we can confirm an asymptotically discretization independent mass. And like I said before, knowing the relationship between the mass and the gate angle is going to be able to tell us some information about the curvature. So let's do this in the 0 temperature case, where we expect the joint mass times this conformal factor to behave as so. So matching this expression to the previous expression in the other slide actually gives us a value of M close to what we expect in the low temperature limit of SYK. And in fact, it's accurate to 3 decimal places. So that's very promising that our reconstruction protocol is giving us some sensible dual that agrees with analytic results. Similarly, in the case of finite temperature, where we don't actually expect to have an ADS geometry, we can numerically find the ratio of the Ricci scalar to the mass squared, which is given by this expression. So this joint quantity, the arc cinch of it is plotted here. And then using that, we can extract this ratio, and we find that deep in the bulk, we actually approach something that looks like a constant curvature, but it diverges near the boundary, and we suspect that this has to do with some boundary UV physics. Next, I mentioned before that the correlators, specifically the commutators of the boundary operators, is going to tell us information about the bulk state. And that's simply because we know that our bulk operators are going to be anti-commuting. And so application of these operators to a state is going to result in only the commutator surviving. And we can simply compute this by taking the matrix of our boundary commutators and conjugating them by K. And so an example here is shown for the bulk commutators as a function of 2 points, and we can recover that data. Okay, next we can actually, because we have an explicit construction, examine the entropy of the bulk fermions along this line. And we observe an interesting behavior as a function of inverse temperature. And in fact, looking at that behavior as a function of our discretization, we are able to extract a relationship for the entropy as a function of beta given by this expression here. So notice that there is a term that diverges in the small delta t limit, but it diverges in a way that actually agrees with known results for CFTs. So there's some constant coefficient for this UV divergent term that we're able to extract, as well as this beta dependent term that controls the entropy density. So next we can probe some more general topological features of our geometry by using the mutual information. And we're going to be exploring this in the regular thermal field double case, as well as perturbations of this geometry. So we're going to see how the mutual information can help diagnose the continuity of this Penrose diagram. So in particular, looking at the mutual information between these two, the fermions on these two sides, you can see that the mutual information, which is actually the difference of these two curves, grows linearly as a function of depth. And that just reflects the fact that as you go further into the interior, you actually get a higher density of points. So this is just qualitative evidence of this thermal field double geometry. But now we can examine altered geometries that occur in the coupled SYK case. So for the coupled SYK model, the setup is simply we have 2 copies of an SYK model denoted by left and right, as well as a coupling between them. And depending on the sign of the coupling, we're going to get different alterations of the geometry. So for mu greater than 0, we're going to be getting the shockwave geometry with a spatial gap. And for mu less than 0, we're going to be getting the traversable wormhole geometry, and we're going to be looking for signatures of the topological changes to this geometry. So again, looking at the mutual information in the shockwave case, we can look at the correlators between the fermions on the 2 sides, and we can actually see decay of the correlation compared to the ordinary thermal field double case, which reflects the fact that in a sense, these 2 are farther apart. A gap has opened up. And then if you look at the mutual information, it actually saturates rather than growing linearly, reflecting the fact that a gap is opened up. And so we don't get that high density of points as you go like closer towards the middle. Now for the opposite side of the coupling, yes, Yes, numerically generate like this. Oh, we are using the analytic results, the large N analytic results, and simply sampling those to obtain the 2-point functions, and then using those 2-point functions to get the kernels and everything else. So in principle, you could actually do this for finite N SYK as well. But in finite N SYK, you don't actually have generalized free fields, but you get an approximate version of Wix theorem, which means that your bulk operators that you recover only approximately satisfy the Wilk algebra. So that's actually some ongoing work that we're looking at now, like what statements we can make about finite N SYK. Anyway, hopefully that answered your question. All right. So you can do the same thing in the negative energy shockwave case in which we expect to get a traversable wormhole. Now, and the calculation of the 2-point functions in this case would actually result in a periodic 2-point function, which would result in an anti-commutator matrix that's singular. And we know that we can't perform the QR decomposition in the case where it's singular. So that actually tells us that our geometry terminates and we shouldn't be looking any further. And the way we look at this is we actually look at the inverse kernel, and this regime where we see a very dark blue is where we actually get zeros in the determinant of the kernel. So this is telling us about the fact that we've opened up a gap and have this like finite geometry. All right, so a summary of what we've done is that we've established sufficient requirements for construction of a local bulk quantum circuit representation for a boundary model with generalized free fields. And this is enabled so long as your boundary theory anti-commutator matrix doesn't have a singularity. And if it does, that might be giving evidence of some topological changes to your geometry. We also noted that we were able to get rid of the requirement of conformal symmetry in our boundary theory. So we can do all of this at finite beta and be able to study holographic duality away from the usual regime. And we also observed that the protocol can deduce geometric features of the bulk circuit, such as the stretched horizon, curvature, and some topological features of the geometry. And some open questions and future directions that we're going in are given here. So the first question is, can we analytically continue the bulk quantum circuit to the black hole interior? Is there a way that we can do that with some general guiding principles? You can also ask the question of, can we potentially run our protocol in reverse and be able to study a candidate boundary theory for de Sitter by examining the 2-point functions in a de Sitter patch? Another open question is, in the higher dimensional generalizations, how do we actually ensure the correct operator algebra, since that comes in the form of a constraint on the shape of the kernel and it becomes less straightforward if you have higher dimensions, what the non-zero entries should be. You can also talk about relaxing the requirement for generalized free fields, such as in the case of finite and SYK, and that's something we're looking at right now. And lastly, some nascent work that I've started with another graduate student is being able to apply this protocol in a completely different context, which has applications to condensed matter physics. And the idea is, can we explain hydrodynamics geometrically by finding which modes fall into a bath and don't contribute to late time dynamics? So we found in our protocol the emergence of this bulk bath that behaved like a horizon that ate up the infalling modes and didn't affect late time boundary correlators. And if we can find an analogous thing in hydrodynamic many body systems that could enable us to be able to more precisely write down what the relevant and irrelevant operators are for hydrodynamics. And that's all I have to say, so thanks for listening.
I have a question in the earlier page for the
you said the traversal.
I'm
okay.
confused by the blue. So does this mean that you can reconstruct the whole blue region from just one boundary?
No, yes. Well, in general, given a single boundary line, you can reconstruct pretty much the entire causal wedge. So that's always true. But as soon as if you consider the case of adding essentially boundary time points, as soon as you get a recurrence in your anti-commutator matrix, you get a singular matrix, and so you're no longer able to perform the decomposition. So that tells you that there's a chance that your spacetime terminates, or maybe there's a bad point. We're not able to distinguish between those two cases until we sample more and more points. But since we already know that we have a periodic 2-point function, we know that it's going to terminate and look like this. And this is the inverse kernel, right? Because we can't invert it, so we're actually plotting a heat map of actually condensed information of the inverse kernel here. But this is the regime in which we have these singularities. Hopefully, does that answer?
Oh, okay. So how about in the leftmost picture? What does that region correspond to? You can just reconstruct the whole
yeah, not the whole thing. So so this region corresponds to the fact. So now, if you have a traversable wormhole, you're going to be getting that singular matrix. So actually, you should stop right there.
Oh, okay.
Yeah.
So you started out with the motivation that HKLL, you have to put in the metric explicitly. But if I understood correctly, it was a requirement in your procedure that you needed the algebra of bulk operators on a Cauchy slice. Should I be unhappy with that? Is there some hope of replacing that with something that has less of a fundamental bulk description?
I don't think you're going to be able to replace it with anything weaker, because a bulk causal structure is kind of the minimal ingredients to have a sensible bulk. We want our bulk theory to be causal and local, but I think that's pretty much the weakest thing that you can get away with.
Okay, but for example, the bulk algebra should contain information about the number of space-time dimensions I have, and that would be nice to derive.
Yeah, well, I mean, at least I'll mention that it suffices to impose the algebra on a Cauchy slice.
Right, but then
and everything else follows. So yeah, I guess whether or not you're happy with that is a personal matter, but I think that this is a pretty weak and natural requirement to impose.
Yeah, I have a couple of questions. So at one point you showed something where you got an error of 0.005.
Oh yeah.
So I just want to understand what you're comparing are you comparing to a continuum? Is this a discretization error?
It could be due to finite size effects. So here we're literally comparing the value of the analytically predicted value of n, which is 1/2 minus 1/2, which is the conformal dimension in the SYK case, to the case that we were able to extract through this extensive procedure, which I tried to outline here about being able to find the joint m times omega and extract its behavior by comparing it to the flat case. I can go over the more technical details of that with you.
But is it fundamentally a discretization error? Is there a continuum limit of your thing that would where that error should go to 0?
Perhaps that's something I guess we haven't investigated thoroughly, but that is something that we could look into. But I guess already it being pretty close is pretty enlightening. But yeah. That's something we can try to.
But you would expect in your system, because you've discretized.
Yeah. And actually, in fact, well, there's a couple of sources. There's the discretization, but then there's which ultimately leads to. Yeah, so we have the discretization, but also in being able to extract the expressions for m and omega in the first place requires us to write down this unitary for some time delta t, and we are finding this in the limit of in a particular limit. So we are writing down approximations for this and then performing some fitting with our numerics to extract the M.
I have a second very basic question.
Yeah, sure.
When you talk about the thermal field double, normally we would have two boundaries, but all of your pictures of your tensor networks were always one boundary. I mean, not tensor networks, your discretized bulk.
Well, I mean, yeah, that's just because it's going to be an identical procedure of reconstruction on both sides. So describing how to find the kernels is going to be equivalent. So
But the true bulk in that case would.
it is two-sided. So basically the way it's actually implemented when we do this on a computer is we have some set of boundary fermion operators. We declare half of them to be left, half of them to be right, but we execute the kernel finding procedure with that knowledge and are able to plug in the relevant correlator information of the boundary operators in the thermal field double state and then retrieve the bulk.
But are you making a choice then about the number of sites in the spatial direction separating these?
No, because that's like in principle infinite and we can just, so, right, you can kind of just extend, like you can just find more boundary time points, which will give you more depth in the bulk. So this is why we have to kind of use these like hand wavy diagnostics, like the scaling of the mutual information as a function of depth to say that we have a particular geometry, because you can continue this procedure indefinitely into the bulk.
So
As long as you have access to.
You're not actually working in a finite spatial lattice with two boundaries.
No, it's an infinite lattice with two boundaries, basically. Yeah.
Oh, I see. Okay.
Yeah.
So when you have the thermal field double, it means that the networks will be very small in an infinite part of the space. So
or they'll be spaced closely together. The equal delta Z slices in the circuit are going to be getting closer and closer together in the physical geometry. Yeah.
I see.
I was just wondering, the discrepancy you mentioned with the Ricci scalar, how it started diverging.
Oh, yeah.
I was just wondering, is that the same? Can you track that discrepancy to be the same as the sort of 0.005 discrepancy that we mentioned before, or is that fundamentally different?
No, I think that's fundamentally different because the second case is like, well, in the finite temperature case, we don't even have a notion of semi-classical geometry really. We know it's not going to be ADS, and so like this behavior is just like probing some physics that we don't quite fully understand yet. Whereas in this other case, this error in M is in the zero temperature case. So we actually have a gold standard to compare it to.
So in your talk, you focused on reconstruction from the basic fermion two-point function of SYK. Have you looked at more general operators in SYK? For instance, fermion bilinears?
No, but I mean, that information is like encoded, or you mean two-point functions of the bilinears? Well, in the case where you have generalized free fields, because everything factorizes, like you get equivalent information. But I guess if you wanted to like study, let's say, finite and SYK, that is something you do. We haven't looked at that.
So thanks for the talk. It seems like an incredible result. Do you have any comments about how this discretized bulk will behave under diffeomorphisms or something like a boost?
So, I mean, if you want to define such operations in the bulk, you have to be a little bit careful because you are discretized, but yeah, I mean, so far what we've been doing is we've been trying to extract information about the geometry through bulk correlators. So if you wanted to define some geometric operator in terms of like finite differences, you could probably do something like that. We haven't looked at that too much outside of the stuff that I've described.
Yeah, just a minor comment. So doing this procedure assumes that you should expect Riemannian geometry in the bulk. However, that seems to contradict some facts about more subtle.
Yeah, at finite beta, I mean.
Yeah, at finite beta. So in particular, this particular geometry that you're showing, It doesn't reproduce other links that are defined by the 4-point function. So it reproduces all the links defined by the 2-point function, but it doesn't reproduce links defined by the 4-point function. So it's a little bit, it's probably not.
No, you're right. This is kind of a, this is very much a heuristic value for the like curvature. But yeah, that is a good point.
It's a Zoom question.
Oh,
I would have a question for myself.
okay.
So can you do the large Q double scale model?
Yeah, actually, we even use some large cubes also. Yeah.
So the Zoom question? What kind of Zoom question?
Some data, I think.
Okay, so we're not run out of time for the Zoom question. Let's time American.